In this video, we'll look at the concept of levels in an arrangement of lines. Consider a set of lines in a plane. The level of a point P is the number of lines that pass below P. In the picture, the level of the point P is 3 because there are 3 lines that pass below P. Using this, we can define the following regions. Zero level is a set of points in the plane where the level is 0. For consistency, we also included a boundary in the zero level, so this vertex is considered to be part of the zero level. Similarly, one level is a set of points in the plane where the level is equal to 1. And so on, we can define 2 level, 3 level, and so on and so forth. Notice that vertices can be part of multiple levels with this definition, so this vertex is part of the 0 level, 1 level, and 2 level. And now using this concept, we define the concept of less than equal k level. So less than equal k level is a union of 0 level, 1 level, and all the way up to k level. In this picture, we have shown the less than equal 3 level, which, as you can see from the picture, is the union of 0, 1, 2, and 3 levels. The theorem that we'd like to prove in this video is that the complexity of less than equal k level is bounded by O of n times k. The complexity here refers to the number of vertices of the arrangement that lie in this region. So in the picture, the less than equal k level is denoted in gray, or is shaded in gray. And we like to claim, or we like to prove that the number of vertices of the arrangement that lie in the gray area is at most n times k. First, observe that the proof is really easy for less than equal 0 level. The 0 level is a convex shape, where each line appears on its boundary at most once. And because of that, it's easy to see that the complexity of 0 level, the number of vertices on the 0 level, is at most n minus 1. Using this, we continue with the following probabilistic argument. We sample every line with probability p independently, and we assume for now that p is at most 1 over 2, or 0.5. Let's say that we get a set of lines denoted by S. Now we look at the point P in the original input, and we look at the probability of P becoming a 0 level vertex in the set of lines S. For P to become a 0 level vertex, first of all, we must sample the 2 lines that define P. Since the lines are sampled independently of the probability P, this is equal to P squared. Furthermore, we have to sample none of the lines that pass below P. If there are LP lines that pass below P, then it follows that the probability that we sample none of them is equal to 1 minus P to the power of LP. Since the level of P is at most K, it follows that this probability is at least this much. Now we use the following fact, that 1 minus P to power 1 over P is a decreasing function of P. It's also worth knowing that the limit of this function as P goes to 0 is 1 over E, but we will not need this fact here in this video. Since this function is decreasing, we can write 1 minus P to power K as follows. And now we can look at this inner term inside the parentheses. Since this function is a decreasing function of P, the maximum value, or the minimum value of this function is achieved when P is maximum. Since P is at most 1 over 2, this minimum is at least when P is said to be 1 over 2 in this part of the parentheses. So over here, inside here, if P is 0.5, this term will be 0.5 to power 2. Or alternatively, we can write it as 2 to the power of minus 2 times P times K. So we can show that 1 minus P to power K is at least this much. And so we can obtain that the probability of P becoming a 0 level vertex in S is at least this much. Let's denote the complexity of less than equal K level of P with this notation. Since the probability of less than equal P level becoming a 0 level vertex is at least this much, it follows that the expected number of 0 level vertices of S is at least this probability times the number of less than equal K level vertices of P. However, from this fact that we showed at the beginning of this proof, we know that the number of zero-level vertices of S is roughly proportional to the size of S. So this expectation is proportional to the number of lines in S. However, since we sample each line with probability p, the expected number of lines in S is n times p. So therefore, this expectation equals O of n times p. Now, if we look at this, we obtain that we have proved that O of np is at least something times the complexity of less than or equal k level. Observe that we are free to pick p. We pick p to be equal 1 over 2 times 2 times k. Since k at least 1, this probability is at most 1 over 2, so it respects this condition that we had at the beginning of the proof. By replacing this probability inside this inequality, we obtain that the complexity of less than or equal k level of p is at most n times k.